Welcome to the Data Digest and another Tidy Tuesday summary. In this video we are going to investigate the salary of almost 200 different college majors. It is based on the weekly 1 hour long Tidy Tuesday Screencast from David Robinson, link in the description. We will find out what the most common majors are, spoiler alert, it's psychology, and which major categories earn the most. It is engineering. On top of that, we will run linear models to investigate whether majors with a high proportion of female students have lower incomes. And for that, we will also create a nice interactive plot. There will be a small detour into the world of Boxplots, and at the end, I will quickly answer some additional questions that David Robinson could not address in his original screencast. In October 2018, David Robinson started weekly live screencasts on his YouTube channel, where he would analyze a Tidy Tuesday dataset he hasn't seen before. David Robinson is not only very good at doing data analysis, but he also has a great talent for asking interesting and meaningful questions to a wide variety of different datasets. And the first video was about college major salaries. Here you see the functions that are going to be used during the summary. Let's have a look and judge for yourself if there's anything you haven't seen before or used. This can help you to judge whether this video is worth your time or if you're already familiar with all of these functions. If there's something you haven't seen before, then stay tuned and learn something new. We will use some basic functions for the data checks and data management, some to clean up the variables, or use the gather function to create a new dataset for plotting later. We will use the basic 5 Tidyverse functions, arrange, mutate, filter, select and gather for some data management, and then run some data analysis and modeling with the linear model function. A big part of data exploration is visualization, so we will use a lot of ggplotting, from histograms to boxplots and column bars. So one way to load the data is to go to GitHub, for data science, into the Tidy Tuesday folder, select data, and then this dataset will be in 2018 on October 16th. But if you don't know the exact date of the dataset, you can use the search function and look for college major. And then I would suggest to use the CSV file in a raw format, because now you can simply copy the URL into RStudio. And you can use the URL as the file name. And now you see that there's a recent grads data frame created with 173 rows and 21 variables. A second way to load the data is to use the Tidy Tuesday R package. So you load it via library. And then there's a function called ttload, where when you enter the date of the dataset, you will get an output file, which is a list that contains the recent grads data frame as a tibble. And to use this tibble, you have to extract it from the list. And you do this just by simply accessing the list item by its name, recent grads with a minus. And another useful feature from the Tidy Tuesday package is that with the readme function, you get information on the dataset directly in RStudio. So you will know where it comes from and also what all the variables mean. So that it's ranking the majors by median income. You get the total number of people that graduated in this major. The sample size represents the number of graduates that gave information on their income. And here it's based on only full-time, year-round employed people that work for more than 35 hours per week. We also know how many men and women graduated. This calculates the share of women in each major. Then there's information on the employment state, whether they're full-time or part-time employed. That's also how the unemployment rate is calculated. And then the median and the interquartile range are given for each major. And the dataset contains information on whether at the end of their studies they actually ended up in a job where a college degree is required, or whether they're employed at a position where a college degree wasn't actually necessary. Let's start with investigating the distribution of median salaries of the various majors. For each of the 174 majors, several graduates provided their annual income, which was used to calculate the median salary for each major. And to plot the distribution of these salaries, we piped the recent grads data frame into the ggplot function, There we specify the aesthetic mapping with median salaries on the x-axis and then plot the data by adding the geom histogram. We see that there is an outlier above $100,000 that come from petroleum engineering and that the data doesn't strictly follow a normal distribution. There's a small skew to the right because the mean of $40,000 is bigger than the median of $36,000. Next, we analyze the median salaries by major categories and visualize their individual distributions with Boxplots. For example, there are 29 different engineering degrees which all come with different salaries, and Boxplots are a good way to summarize this data and compare it to other major categories. To do this in R, we again pipe the dataset into the ggplot function, but now map the major categories to the x-axis and the median salaries to the y-axis. We use the geom boxplot for visualization and get a very ugly overlay of labels on the x-axis. There are different ways to fix this. First, we can rotate the labels by 90 degrees by using the theme function, and within the axis text x element change the angle to 90. This already looks a lot more useful, and if you want to pull up the by default centered labels to the x-axis, you can use the hJust argument and set it to 1. Another way to fix the overlapping labels on the x-axis is simply to switch the axis via the coord flip function. A quick way to sort the major categories by decreasing median income is with the FCT reorder function inside a mutate. ggplot by default turns the major categories into factors by alphabetical order, and with the FCT reorder function we can reorder those groups based on another variable, namely the median. Additionally, using the $format function from the scales package within the scale_y continuous function, we can turn the income numbers into a pretty dollar format immediately. Now, one final step to make the graph even better looking is to include the y value with the expand limits y = 0 command, and by specifying a fill within the ggplot function, we can give each major category its own color. The theme legend position = none is used to not duplicate the color coding and naming in an extra legend. And as you can see, the categories that have the highest salaries are engineering, computers and mathematics, business and physical science. So basically STEM plus business. And the categories that include majors with the lowest earnings are education, humanities and liberal arts, and psychology and social work. I would like to spend the next 4 minutes to explain the rules for the whisker length and outlier determination in Boxplots and how they relate to the interquartile range and the normal distribution. Let's look at the numbers from 1 to 100. When we use the summary function, we get the min 1, the max 100, the median, which splits the 100 numbers in a bottom and a top 50, and we get first quartile and the third quartile. The interquartile range must include 50% of the data, so the numbers 25 to 75 represent the interquartile range. And when we plot a box plot of these numbers, we get a graph like this. And in this plot, the whiskers extend all the way from 1 to 100, including the min and the max. Now I set up the plotting to have two graphs next to each other in one row and two columns. And I switch the number 100 for a bigger number, 149 for outlier. And for outlier 2, I switch it for 151. The interquartile range is still the same, so the box includes 50% of the numbers from 25 to 75. But the change now is, in the right plot, you see that an outlier point appeared, and the whisker only extends to around 100 and not all the way to the max, as can be seen on the plot on the left. And this happens because the rule for outliers and box plots is that any point that extends by more than 1.5 times the interquartile range will be an outlier, and then the whisker only extends to the point below that, which in our case is the value 99. Let's turn to a more realistic example where we simulate 1000 normally distributed data points around a mean of 0 with a standard deviation of 1. And if you want to get the same numbers as I do, then set the seed to 3 as well. As you can see in the box plot, in a normal distribution 50% of the data will be around 0.67 and minus 0.67 standard deviations, and you see 3 points in the box plot that extend above or below 3 standard deviations, when you look at the dot plot at the bottom, you see that it's actually 2 points below -3 standard deviations, and I added these blue lines in between where 50% of the data should fall in a normal distribution. Let's check some of the things I just said. The first quartile and the third quartile are at around these 0.67. When we ask specifically which values are above or below 0.67 standard deviations to the left or the right, we get these 50% almost that represent the interquartile range of 1000 normally distributed points. There are different ways how we can calculate the interquartile range. We can either go by the position of the values from the summary function, so the first quartile and the third quartile, or the second and the fifth value the summary function gives, or we can access these values via the names of the summary. So with basic indexing of the summary results, extracting the second and the fifth value, we get the first and the third quartile, and when we use the diff function, we would get the difference of the third and the first quartile, being the interquartile range of 1.36 in this example. And now we want to determine if a point is an outlier, we would have to check the upper limit, which is 1.5 times the interquartile range added to the third quartile. And this would be everything above 2.718. So what we do next is we sort the 6 highest points of our 1000 normally distributed points, and then we use the box plot and zoom in at the y-axis, and I added a black line that's now going to the upper limit, being 1.5 times the interquartile range added to the third quartile, and I add a red line at the point just below that, and then the whisker of the box plot extends exactly to this point and not all the way to the upper limit we just calculated. And now we can do the exact same thing for the lower limits. When we subtract 1.5 times the interquartile range from the first quartile, we get to -2.72, and when we look at the lowest 6 values, we see that 2 of them are below this cutoff, and then we plot it again, zoom in on this area, add the line for the limit below which all points should be outliers, and we add a line to the last point that's within the limit to which the whisker would extend. Now let us look at the individual majors and the amount of money you could expect to earn after graduating. We simply arrange by decreasing median income, select relevant variables to display with the view function to get the following results of majors that earn the most. The top 18 that make $56,000 or more are almost exclusively engineering, with some business and physical sciences mixed in. This we already learned from the previous box plots showing us the major categories that earn the most. The majors that earn the least, and here we are talking $30,000 per year or less, fall mostly into the humanities, arts, psychology and social work. And at the very bottom we have a major from the education category that only makes $22,000 per year, namely
the librarian. Shh. Quiet.
So if you really love books, a quiet working environment and don't really care all that much about money, then library science may be for you. Plus you might get away with occasionally yelling at noisy kids.
I said quiet.
One way to visualize the median of each major is with the geom_point function. Again, we use coord flip to make the majors more readable on the y-axis, but it's easy to improve upon this graph. For one, we can change the all caps spelling of majors into the title format with str to title, where only the first letter of each word is capitalized. Next, we reorder the majors by median income with the fct reorder function. We can additionally color code each major by the major category within the ggplot function, linking the color argument to the major category. And since we do know the interquartile range from the 25th and the 75th percentile, we can use the geom error bar function to visualize the spread of earning for each major. Lastly, we include the 0 value with expand limits y equals 0. In order to make plotting easier, we can create a subdata frame that has some of the editing steps already performed. Here we generate a majors process data frame that has the str to title formatting and the fct reordering for majors by median already done. Another point that should be considered and included here is the sample size. Some of the majors might show less reliable data because only a handful of students were surveyed. Let's visualize this quickly with a labeled scatter plot. We put the sample size on the x-axis and the median income on the y-axis. For example, majors like library science, soil science, pharmacology, mining and mineral engineering, educational psychology or botany were all covered by less than 10 respondents. With this in mind, we should revisit the previous graphs for the top and bottom 20 majors and redo them based only on majors where at least 30 graduates were surveyed. This graph you already saw, but now we use the process data frame and filter for a sample size of 30 or more. Select the top or bottom majors with the head or tail function and give it a proper title and subtitle within the labs function. There are different ways to count the major categories within the Tidyverse. The count function creates a data frame, or table to be more precise, with the variables we specified within count and an additional n column that holds the frequency of each major category. And with a range we can sort the result by descending n. The same result we get without the range function by simply setting the sort argument of the count function to true. With this approach, we are only counting the number of different majors within each category, showing 29 different engineering degrees existing in this dataset. A better way to count how popular each major category actually is would be to take the number of graduates into account. This we can do by weighted counting using the WT argument and giving it a second variable, in this case total. Now the total number of graduates from the 29 different engineering degrees are summed up to give the engineering total N, which is a bit over 500,000 graduates. And that is not enough to make it into the top 3 most common major categories, which are business, humanities/liberal arts, and education. Let us visualize this finding with a basic bar chart using the geom call function. We have to use FCT reorder again, otherwise the bars would come out in alphabetical order instead of decreasing n. We put major category on the x-axis and the n variable from the weighted counting on the y-axis, and then flip the coordinate system as before. And an easy way to make this graph a bit more colorful is to set the fill argument within the ggplot's aesthetic mapping to the major category variable. But instead of simply giving it a rainbow touch, we can actually include another variable into the bars. We could add the gender split to the graph by using the gather function. I'll explain its detail once we come to the most common individual majors, but for now it's enough to notice that a gender column gets created with men or women as entries, plus the number column which holds their frequencies. We now have to use numbers for the y-axis instead of n, and we can use the new gender variable for the fill argument within ggplot. Also notice the labels equals comma format function within the scale y continuous that turns big numbers into a proper format. Let's plot the most common individual majors. We reorder them based on the total number of graduates with FCT reorder, arranged by decreasing number, and then only focus on the top 22 for plotting. We can color code majors from the same major category by using the fill argument within ggplot. The rest of the functions were used before, and now we see that psychology was the most common major studied in 2018. Second place is business management and administration, and thanks to the color coding, we can find other business degrees quite simply. General business on the 4th place, marketing and marketing research, as well as accounting made it into the top 10. And in case you wondered why I said head to 22, without that there wouldn't be any of the most profitable majors included in this graph, as none of the engineering degrees were in the top 20 when considering the number of graduates. Gather basically turns a wide data set into a long one. In this example I show 26 rows of the most common majors, and you can see the number for men and women in separate columns. If we want to use this information in ggplot, we have to turn it into a long data frame, with one column named gender that takes the variable name from the man or woman column, and a second column called number that holds their respective values. As you can see with the dim function, we now have a data frame with 52 rows, where the first 26 hold the numbers for men, and then the majors repeat at row 27, starting with psychology again, but now with the numbers for women. And now it is fairly easy to plot this by using the number variable for y and the gender variable for fill. As you can see, business for example is almost a 50-50 split, whereas psychology has around 80% women, and for nursing and elementary education it goes up to roughly 90%. On the other hand, mechanical engineering and electrical engineering are 80 to 90% studied by men. Now we will investigate the correlation between the share of women and median income. First by looking into major categories overall and afterwards into individual majors. We do this by using the group by and summarize functions that give us a total number of men and women studying the major category and the newly calculated share women as a percentage of the total. We also produce an average median and a median weighted by sample size of the individual majors. Here you see before and after images from 3 selected major categories. With group by and summarize we combine the 5 law majors, 4 communication and journalism majors and 8 art majors into 3 separate groups holding the major category totals and averages. And this will then be repeated for all the other majors and categories as well. Here's the result. For law and public policy the weighted median is 36,000, the value from row 3 pre-law and legal studies, but is weighted down by the bigger sample size of criminal justice and fire protection, where 1,728 students provided income data. Not much difference for communications and journalism, as those median salaries are all very close to each other. And for arts you get an unweighted median of 30,750, which is between music and fine arts. However, this value gets a bit pulled up by the commercial art and graphic design degree that had over 1,000 students profiled and came down at a median of $35,000. The miscellaneous fine arts that are at 50,000 have almost no influence, as they only have a sample size of 30. Let's plot these summarized values with women percentage on the x-axis and median weighted salary on the y-axis. The basic version gives us 16 dots that seem to follow a downward trajectory as the share of women increases. Here's how we can improve this graph. We add a geom_smooth method equals LM to show how a linear model would fit into these 16 points. geom_text_repel will add the major category labels to each point, and thanks to the repel force will move text away from other text if necessary. Before drawing any conclusions, David Robinson suggested to investigate this further by looking into the individual majors data as well. We now run a linear model where we try to predict the income based on the percentage of women of all majors. The summary results show that the intercept starts at $52,073, and then every point you move up in share women, you go down by $23,650, which in percentages mean going from 0%, where the intercept cuts the y-axis, to 100%. In other words, for every percentage point increase of women, the model predicts $236.50 less annual income. We can get a basic graph with geom_point and geom_smooth to add the linear model. This can be advanced by using color equals major category within ggplot. When we add major category information, we have to be careful as to how to run this model and specify group equals 1 within geom_smooth. The group equals 1 argument makes an interesting point. The reason why the income goes down as a percentage of women increases is multifaceted. When we look at the total number of graduates by gender, we see almost 4 million women and almost 3 million men graduating. And one could oversimplify this result by saying more people studying something decreases the demand, which leads to higher competition on the side of the employee, which allows the employer to lower the wages to fill a position. Here David Robinson suggests to run this linear model within each major category, similar to how the graph on the left side looks without the group equals 1 assignment. And there you can already see that some income lines are going up as the percent of women increases, or stay perfectly even level over a wide range of different women percentages. I won't explain all the mechanics behind the nesting and mapping, but with these few lines of code we basically create a linear model within each major category that has at least 10 different majors. And at the end we adjust the p-value with a false discovery rate method to protect against multiple testing issues. Here's the result. Most of the estimates of the slope predict a decrease of median income when we go from 0 to 100% women within each major category. For example, within engineering and based on 29 different degrees, the income reduction comes down to $33,912. Within health, there seems to be an opposite effect, as the income increases with higher percentage of women. However, given the relatively small sample size, none of these results are statistically significant when considering an alpha of 0.05. Some of the p-values are below 5%, but after being adjusted for multiple testing, increase to roughly 10%. Here is a fast way to make an interactive graph that you can use for data exploration. All we have to do is save a ggplot object and later call it with the ggplotly function. One cool trick is to use the fct_lump function within mutate that will keep the most common 4 major categories and lump the rest together as other. If you found any of this helpful, please consider leaving a like. This is my very first video, and if you want to get notified of new and hopefully better ones in the future, please subscribe to my channel. I took 2 screenshots from the interactive model, one while hovering over the nursing major that is 89.6% female and has a $48,000 median income and is far above the trend line of the linear model. And the second screenshot shows a point that is far below the trend line and comes from theology and religious vocation, which, based on the linear model and the low percentage of women, should have a higher income. Before we get to some additional questions and answers that David Robinson could not address during his original screencast, here's a quick way to visualize the data with respect to median income and unemployment rate. Now let us ask some questions that couldn't be addressed during the original screencast. For example, if you're pretty sure you want to be an engineer, so that's the major category you're going to study, then what special area should you go to when the unemployment rate is really important to you? So let's call this job security and simply filter for engineering as a major category and arrange by unemployment rate. And then select some interesting columns to investigate and view the whole thing in RStudio. So now we have 29 different engineering degrees sorted by unemployment rate, and overall these are pretty good looking. The overall unemployment rate is 6.8%, so most of them are below, some even below 1% with a good median income. And some of the top majors in engineering are areas that aren't studied by many people, so these are all in 1,000 ranges, and then they are below 4% unemployment rate, like engineering, mechanics, physics and science, petroleum engineering, material science. Then more common engineering degrees are in the middle, where we get into the tens of thousands, from mechanical engineering to electrical and general engineering, chemical engineering down to computer engineering and civil engineering. And here the unemployment rate is in a range of 6 to 7%, with median incomes around $60,000 per year. At the bottom, maybe surprisingly, we have nuclear engineering. This might be due to some states abandoning nuclear power plants. And also, quite interestingly, architecture studied by many students, 46,000, which leads to a somewhat higher unemployment rate of 11% and also a rather low median income. So when you're passionate about architecture, be aware there's quite some competition and not too many positions available. The following question might even be more relevant than the unemployment rate overall. The dataset contains information on whether the graduate ended up in a job that needed a college degree, or whether they end up in a job where the college degree wasn't even necessary, or if they end up employed in a low-wage job. To figure this out, I calculated the percent college jobs by dividing the college jobs by total number of jobs and then multiplying by 100 and rounding to 1 digit. And I repeated the same for non-college jobs and low-wage jobs. We again filter for the major category being engineering, arrange by unemployment rate, and then look at all these newly created columns. So for the major with the lowest unemployment rate, engineering, mechanics, physics and science, already a quarter of the employees ended up in a job where the college degree wasn't a requirement. So let's sort for some of the extremes. The majors that lead to very high percentage of college jobs are very specialized majors, like material science, naval architecture and marine engineering, materials engineering and material science, and geophysical engineering. So once you graduate in these majors, it's almost guaranteed to end up in a job that required specifically this degree. On the lower end, we have more general engineering degrees like engineering, industrial management, industrial production technologies, where only a third of the graduates end up in a job where this degree was necessary, and half of them end up in a job where a college degree wasn't a requirement. And if we thought by low wage job percentage, then industrial management and engineering is on top, followed by architecture and nuclear engineering. Nuclear engineering and architecture had rather high unemployment rates, so some of the graduates already have to live with a low wage job or a job where a college degree wasn't necessary. Finally, let us investigate the interquartile range. For this, we filtered the majors by a sample size of 10, so at least 10 graduates provided an income. To calculate the absolute interquartile range, we simply subtract the 25th percentile from the 75th percentile. I think it's also worthwhile to calculate the relative interquartile range by dividing the just calculated absolute interquartile range by the median income, and I round it to 2 digits. And then we select some variables and simply look at them with the view function. Let's look at the highest absolute interquartile ranges as first. These usually make big differences because they represent majors where you can either go into academia and earn maybe $30,000 a year, or for astronomy and astrophysics you go to NASA or work for private companies and then maybe make over $100,000 per year. Same holds true for the pharma industry. The smallest absolute interquartile range is seen at court reporting, where you make a decent $54,000 a year, but the range is virtually non-existing, so everyone makes almost the same. And in social work or counseling psychology, the absolute interquartile range is very slim, so you will end up earning very close to the median with very little spread. When we look at the relative interquartile range, we already saw court reporting doesn't have much of a spread, but petroleum engineering is second, even though it has $30,000 as absolute interquartile range. Because of the median being so high, the interquartile range is rather small. And the biggest interquartile ranges we also already saw in the pharmaceutical industries and astronomy and astrophysics, where the range between the 25th and the 27th percentile were rather big, and giving the median income not being so high, it leads to very high interquartile ranges.